Long ago, in a far-off realm, a legend was told of a castle, a dragon, and the design of a clever engineer who designed a drawbridge to break from the weight of dragons. If a dragon were to ever attack the castle while the drawbridge was left down, the heavy weight of the serpent would snap the chain, sending the drawbridge and the dragon with it into the moat below. There's the drawbridge, there's the chain, and there's the pivot where the bridge would be swung about on an axis. This is a story of balanced torques. By canceling our torques, we will learn how to check if the chain will break. That is the dragon at that distance from the pivot too heavy for the chain to hold? And thus, will the castle be safe? Well, what we first need to know is the weight of the dragon. But to analyze torques, we need to know where that weight, that force is. So the distance of the dragon from the pivot to the weight is the position vector that gets calculated to create the torque of the dragon. Because torque, as you know, is distance times weight times the angle between the position vector, the distance, and the weight. In this case, the angle between the distance of the dragon from the pivot to the weight of the dragon is 90 degrees. Those vectors are perpendicular. So the torque of the dragon is simply the distance from the dragon from pivot to its center of mass times its weight. Now the tension from the chain will create another torque because it acts at a distance from the pivot, where it pulls up at the distance dc, the distance of the chain from pivot, and the angle those vectors make between them creates the torque of the chain. The distance of the chain times the tension and the sine of the angle between those vectors. Now that angle between the vector, that t sine theta, is the perpendicular component of the torque. Because that's what a torque is about, is the perpendicular component of a force times the position the force acts from a pivot. Thus, is the torque of the chain equal to the torque of the dragon? It would be, but there's one more torque from another force acting at a distance. That drawbridge has a mass. The center of mass of the drawbridge is where the weight of the drawbridge acts. So the distance that the center of mass is from the pivot and the weight of the drawbridge is another torque. The torque of the drawbridge is equal to the distance of the center of mass times the weight and the angle between them. And again, those vectors are perpendicular, so that equation collapses down to distance times weight, distance of the center of mass times weight of the drawbridge, is our third torque. And those three torques, the two counterclockwise torques of the dragon, the counterclockwise torque of the center of mass of the bridge, is equal to the clockwise torque from the chain. This is because all our torques add up to zero. The clockwise torque from the chain is equivalent to the two counterclockwise torques from the dragon and the center of mass of the bridge. Now, for this to be in equilibrium, static equilibrium, the forces also have to add up to zero. Our three forces, we have two down, the weight of the dragon and the weight of the bridge, and the tension in the chain, perpendicular, pulling up. Well, do those three forces cancel out? When you do your calculation, you'll see they don't. Thus, is there a missing force? Well, what else is the bridge in contact with? Well, the axle, we're at the pivot, where the drawbridge swings about. So the force of that pivot, is the force of that pivot positive or negative, is up or down to cancel out the other forces? And what is its value? Well, given these values here, the weight of the dragon, the weight of the bridge, the length of the bridge from pivot to end, the chain is attached 2 meters from the pivot, the dragon sits 13 meters from the pivot, and the angle between the chain and the horizontal of the bridge is 23 degrees. And the center of mass of that bridge, where the weight acts, is 7 meters from the pivot. Thus, the first thing you'll turn in for this information is calculate the tension in the chain. then is that tension exceeding the maximum tension the chain is able to hold? 500,000 newtons. That is the drawbridge designed by that engineer going to be safe from the weight of the dragon? Will the chain snap to send the drawbridge and the dragon with it down to the moat? Now, we broke that tension into its component perpendicular to the position vector of the chain. But that means if we broke it into a component perpendicular, we have a component parallel or horizontal to the drawbridge. So what about that pull, that parallel pull? Well, if our forces add up to zero, we must have that parallel tension, the horizontal tension pulling in towards the castle, the bridge being pulled into the castle, must be balanced out by the normal force of the wall on the drawbridge, or from the axle or pivot, whichever it will be, to balance out that parallel component of the tension. Thus, the third and fourth thing you'll turn in is the force of the pivot and its amount and direction, and that tension horizontal. Now, that normal response of the wall back onto the bridge creates a stress or a pressure onto the material of the bridge and the pivot, but that's a story for another time.